Good afternoon and welcome to ICE webinars. Today we are joined by James Freeman, multi-vendor modality manager for CT, PET and nuclear at Philips Healthcare. James has decades of experience in the medical imaging world, in particular computed tomography, which has been both a professional and personal journey. ICE webinars would also like to thank AllParts Medical. AllParts Medical provides multi-modality, multi-OEM replacement parts from its facilities in Nashville, Tennessee. In addition to part sales, AllParts also provides customers an extensive array of in-depth training classes and technical support before and after the sale. An ISO certified quality management system helps deliver an industry-leading warranty rate. So for more information, please visit allpartsmedical.com. Now, just a reminder to save the date for our 2026 ICE Expo, which will take place at the San Antonio Marriott River Center on the Riverwalk, San Antonio in Texas. That will be February the 20th to the 22nd. The Imaging Conference and Expo is the only conference dedicated to imaging directors, radiology administrators, radiology technologists, and imaging engineers. ICE offers valuable CE credit from the ASRT and ACI and is a unique community of key decision makers and influential imaging professionals. So for more details, please visit attendice.com. Okay, today's webinar, as usual, is eligible for one Art Category A, CE credit by the HRA, and you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your one CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. We'll be wrapping up today's presentation with a live Q&A, so please submit your questions anytime using the questions feature on the webinar dashboard. Let's kick off today's webinar by giving away one of our ICE gym bags to the attendee that can tell me the answer to the following trivia question. August is National Eye Exam Month. What is the most common eye colour? Answer now using the questions feature on your dashboard, and I'll reveal the answer at the end of the webinar. As I mentioned earlier, James Freeman is our presenter today, and he will be discussing CT essentials, an introduction to CT and emerging technologies. So James, you may begin whenever you're ready.
Thank you very much, and good day to everyone. I hope you're having a good day. Obviously, we've had a great history with CT and its value to the market and imaging and taking care of people. So it's been a career for me in many ways. And I'll bring on the next slide here. There we go. So a little bit of my background, we'll talk about that, descriptions of CT, computerized tomography. As computers have improved, so has our ability to do better diagnostics with CT, and then we'll go through service, the cost to serve, elements to consider, how CT tubes are one of the biggest things that we have as concern with and need for service, and then what CT supported AllParts means as well. So my personal story with electronics started in the 70s. I worked on radar at F4 Phantoms, basically since 76. Started with GE in 82, X-ray products and CT products. So the CT product in those days was an 8800 CT. That was really an adapted X-ray generator and Data General S200 computers. So it goes way back. And the processor was that we had 96K of RAM, 200 megabyte hard drive, and one slice rotation of the gantry was 9.2 seconds. So things have improved dramatically since those days. So I've basically been involved with CT since 83, all the way up to currently. But also my family members, myself, have been scanned with CT. So we understand the imperativeness of what it brings to the diagnostic industry as far as patient care. It's very important, and I hope some of you may even be interested in that in the future. I had the fortune of installing some of the first CT scanners at some of the hospitals in the area that I lived with. In that endeavor, I was very fortunate. I had a friend that was a physicist who later on would do surveys for CTs and stuff. and during the installation of one of the scanners, he and I actually stayed after hours, and we walked through what physicists were looking for, how they ascertained the value of the machine from a quality perspective. So I was very fortunate to have some of those inputs outside of even the company that I worked for. So my history is with CT, electronics, computers. Not only is it part of my job, but it's things that have interested me and allowed me to stay in this position. So we can each impact people's lives through just being able to do service on these products as well. So that's something that I have valued as well. And even though I had late hours, sometimes my wife understood the value and my family of what we brought to helping people at the hospitals. So where's CT used? Typically hospitals and clinics. Hospitals being the first, and especially within ER, and then clinics as well, right? So emergency, and urgent care was one of the first things. Especially looking at head injuries. Neurology being one of the first. CT was the first device that could image brain tissue. An X-ray room, you could have a 2D presentation, but unless there was a metal or something within your head, you wouldn't be able to see the lobes of the brain or anything else until CT came to market. Angiography, flow studies, all those things can be done with CT as well. And then obviously the abdominal and pelvic area, and then radiation therapy planning is part of CT as well, to really leverage oncology and plan for different doses from different directions. So why CT? As I discussed earlier, first device to do brain tissue. So Dr. Hounsfield invented CT in England in the 70s, late 70s. It started to come to market, and the first scanner that came out into the market was a brain-only head scanner. Nowadays, we can do even 3D images of a whole body if the scanner is capable of what we call isotropic imaging, which means X, Y, and Z. And Z being the biggest issue for CT over all the generations, the thickness of the slices on the Z axis was the table goes in. So the first imaging device, like we talked about, for brain. But also we do something very exact. We don't just display an image. We display an image based on CT numbers. So those CT numbers represent different materials within your body. Air, blood, water, different body materials have known CT numbers. The scaling system is based on air being one element and then water being the other element. When we talk about water, it's distilled deionized water. That is what we represent on a scale. So on a daily basis, we have to do air cals to update the air every day because of barometric pressure, temperature, a number of air elements within that. So air is updated daily to adjust for any compensation with that while we scan. So we talked about the advantages. The disadvantages, obviously, is we have higher dose. And with that dose means we have to have a better benefit than just having a higher dose. So when you talk about X-ray, we're doing a 2D image. We're making one shot, maybe head first, and then one lateral. But either way, that's only 2 exposures. We're doing at least 180 degrees worth of exposures to have enough data to represent an image in CT scope. So that's going to be the value, that the fact that we can place materials a little bit more accuracy, and then we can differentiate different tissues from each other very well, allow CT to be very leveraged for a lot of different things. So the dose is definitely higher. You want to limit your exposure to CT, but the advantages of it are exactly what we just happened on the new slide, is neurology. So with that, we could scan ahead. In this case, you see on the top a person's head. You can even see the lenses in your eyes, as you can see. The bottom images have more contrast introduced, so you can see vessels as well. So this is known as a study of brain with and without contrast. And we have processed this with soft tissue in mind. We can process the image with bone as well, algorithms. So we'll talk about the algorithms a little bit shortly. But notice that you can really see what's going on, even with the sinuses, around the optics. And we don't have a picture here, but you can even look at the inner audio canal on the sides. So we can look for tumors, you can look for hematomas, all these things, hence the reason why it's leveraged for trauma in ER systems as well. So with regards to pulmonary, you can look at lungs, so we could see the heart. So in the top image, we're looking at two different images, one with the lungs in mind and the other one looking at, looks like the heart, okay? And you see just all the bronchial tubes, all those details. So we can really get great accuracy here, right? So we can look at tumors, dimensionally look at them different directions. Nowadays, they can even take that data and produce a 3D printed image of a tumor before they even go to surgery if they want to figure out how to approach getting to that tumor. So when we have really good depth on Z, the image on the left is artificially colored. We don't have color in CT. We have CT numbers. So it's false colored based on which CT number they want to represent as red, and others as well. But you can see the spine, you can see aortic, and you can see the heart here as well. There's some movement in the image as well. That's kind of false colored into the green as well. On the image on the right, that's one slice represented. As you can see, very good detail, okay? We could gate a heart study so that we basically freeze the heart in place as we're rotating around. This gantry would rotate much faster than normal so that we can have samples of data and then eventually have enough data for 180 degrees of projection to give us what would look like a heart. So again, we have different CT numbers that are represented in grayscale. So here you see a great makeup of what we see in the body. We have gas in our body. Obviously, we have air. So all these things will have a particular CT number of attenuation. So it allows us to leverage quite a bit. So we're very sensitive with regards to the numbering system and how we validate and do QA. So, it's much more specific in the way that we deliver the information to the screen. What you see on the screen is grayscale representing different CT numbers, and we could change that as well. So for the first time, obviously, we can look at for bleeds, for cancer, and a number of these elements as well that we see in the liver. And it's very interesting to be able to look at images and see the detail that we can get nowadays. So even lumbar spines, sometimes they'll be done with an MRI, but interdisc spaces and having for spine surgery, looking for a disc intrusion into the spinal nerve has been quite interesting to see a lot. I've actually been CT'd and MR'd for back surgery, so I understand how much it can relieve the pain, but at the same instance, how leverage these technologies allowed. Think just 50 years ago, we didn't have these technologies that would allow us to do some of these things. So when we look at a CT scanner, there's a number of generations, and I know that people kind of like related to an iPhone 1 versus iPhone 15. That's not really what's going on. We talk about CT generations. It's basically the way that we acquire the CT image is a little different with the topology. The scanner that you see here is what we would call a third generation scanner. That is where the X-ray tube and the detector both rotate around the patient. And first generation, second generation would translate a smaller detector, but laterally move the tube and the detector laterally through the patient. And the second generation had fewer more detectors. This was third generation. There's also a fourth generation where the detector ray was 180 degrees all the way around, and the tube and the collimator rotated around. But multi-slice in the fourth generation space would be too expensive to have a system in the market. So third generation is what all current scanners are. Fifth generation scanner was electron beam tomography. EBT as it's known, and that was best done with cardiac studies before scanners got fast enough in get rotation to be able to take over that duty as well. So we have the X-ray source, the fan beam represented in green, and a detector array. The detector array is a crystal that will take the X-ray photon and convert it into light for a photodiode to pick it up, and then that photodiode will be digitalized. So the next slide you have here is basically, if you think about it, we're rotating around a patient. So we're creating a volumetric cylinder of data. And then through that data, this is both helical scans here. We used to do axial scans where the green would just be a straight slice through and then we'd advance the table. Now we're doing a helical mode. And so the one on the left would be considered a pitch of 2, where we have data basically for every 180 degrees. If we had the green slices adjoined each other, it would be a pitch of 1, and we'd have data set for 360 degrees, which would be better and reduce the noise in the image. But to compensate, we can raise MA to have a higher dose that would give us this pretty close to 80% of, or 85% of the same equivalent of an axial or pitch of 1. On the image on the right, now if we had a 4-slice scanner, we could fill that volumetric data set up faster. So then we progress on from 4 slices to 8 to 16, 64, 128, 256. Depending on the type of study, that benefit would be you could do a whole heart now with a 128, 256 type scanner. There's even larger ones for doing cardiacs where they could go around basically 3 or 4 rotations and have your heart completely data set for your heart completely done for recon. The first 4th generation 4-slice scanners came out in 1998, and that's kind of scary. So how do we produce an image? The first corner over here, the upper left, that is what we're basically scanning. And as we push X-ray through with the green arrows, this is what the detector would see within grayscale, would be on the left side. And then if we push the data with the X-ray tube and the detector vertically, then you would see as the yellow arrows point down, we would get a sample in grayscale as well. So what we have in image number 2 is if we take and push that data back through a grid, originally the grid size in math grid, right, and within the computer, we would push this back, the data back. This is called back projection. As we push more and more data back from different angles, we start to represent more of what was scanned. So this is known as back projection in the process of CT. As we approach more and more angles, we more represent what we saw. So in slice 30, image 32 here, with 232, we basically have a lot of ghosting and stuff. So in the process itself, when we do CT reconstruction, we have what we call inherent artifacts that have to be cleaned up. So in doing that, we would then add a filter. So all scans are done with a filter applied. Think of this as a frequency response filter, where maybe we have the data of this one side on the left side. I'm sorry, let me go back. The left side, we would have this as far as data collected, which would represent this little spike in blue here on the left side. As we add a filter, aka a low frequency response filter, a mid, or a sharp, the smooth filter would be that if you take into an example soft tissue, like the difference between liver tissue and kidney tissue, that's a small change in CT number attenuations. So if we want to see small changes in that would be a low frequency response filter. We would kind of enhance that. Whereas if we're looking at bone and fractures in bone, we're doing a bone algorithm or a shark algorithm. So we basically take this data set, we run it through a frequency filter, fast Fourier transform, and then we do an inverse fast Fourier transform to have what we would say the data set would look like here. So this inherent artifact introduction that we have is these negative going spikes were never in the data, but they still show up in the image. And here you see the light edge of basically dark or black lines here that wasn't originally in the image. But that's part of the image artifact that's known to be part of a CT image reconstruction, inherent artifacts. So with a filter applied, again, we back project the data with the before we even project the data back, we filter it first. Okay, and then we basically, as you can tell from a number of the slides here, each one reproduces a better quality image. So 128 with the filter applied, 128 without the filter. So with regards to that, we'll always have a filter applied. By default, most of the manufacturers have what we would call a standard algorithm. So if you don't pick one, there's going to be one applied automatically. That'll be a mid-range filter. Now, why is this important? That raw data that we saved or scan data we saved still resides on the hard drives. If we go back and change to a different filter, we could do a soft algorithm for brain tissue, looking for bleeds, hematomas, those kind of things. And then we could go back with that same data set, not even scan the patient, reconstruct it with a sharp algorithm, dense bone, maybe a bone fracture or some other issue with the skull. And you would have both data sets from one image acquisition with the patient. So this is a benefit of CT, where if you have a car accident where someone may hit their head on, the windshield or whatever, you're looking for hematomas, you can see the soft tissue side, then reprocess data with regards to the bone or any skull fractures or anything like that. So it gives us a versatility to reprocess the same data set many different ways to enhance, aka the changes in CT number or frequency response of those CT numbers. So we have the scaling system. Dr. Hounsfield invented it. So it's the Hounsfield scaling system, otherwise known as CT numbers. So they're equivalent. So as the scaling system works, most of our bodies are made of water, right? So water is the center of the scaling system. Air is minus 1,000, which is the least attenuating. And then bone approximates 1,000. It's in the high 900s. Okay, and so this is how every one of those materials is basically converted into a number based on its attenuation coefficient. So if we break those Hounsfield units or CT numbers into a scaling, where air is at the bottom of the scaling system and up, if you notice from a plus 100 to a minus 100, if we break that out as water's in the center, you'll see that most of our body tissue, other than bones, falls within that range of plus and minus 100. So there's known CT numbers for blood, for gray matter, white matter in the brain, kidneys, those things. So if something's an outlier, it's going to be a different CT number than the ones that we've got. So with regards to quality assurance, we have phantoms that we scan that represent those different materials so that we can validate with a test phantom that our system is properly reproducing those different CT numbers. So we care about the CT numbers, the accuracy of those within about scientific method, about our error about 3%. So we have to be within that range. So notice that we're very concise, and that will show up as we represent this grayscale in the display. So when we scan a patient, we not only have X and Y, which you see here as far as a grid, we also have the depth that represents. And if it was a 5 millimeter slice or a 1 millimeter slice, that would be the average of those CT numbers in that depth. So as we approach what we would call isotropic imaging, the depth of the slice would be the same as X and Y. Okay, so this is showing a grid of 512 by 512. And with that, the newer scanners represent a 1024 by 2024 matrix, which basically is 4 times the data set. So what you're looking at is a CT number being in each one of those voxels, and that being represented in a grayscale. So same image exactly on both left and right. The difference is which CT numbers we wanted to represent in grayscale. So we didn't reprocess them at this point in time to enhance anything. Same algorithm is used. The difference is the level and the windowing is set more to represent what we see air and soft tissue on the left, and then we're looking at the heart and other soft tissue elements on the right image. So exactly the same scanner, just the window level were changed. So what that really says is behind the scenes of this window level setting is a digital number represented in every one of these pixels that we're then conveying into a grayscale representation. So ACR Phantom is used in the United States to validate CT scanners. Notice you'll see materials in here that we represent are used to qualify the value of a scanner. ACR is done twice every 2 years. So a physicist will come in, validate the protocols that were scanned, patient scanning protocols, and to validate image quality. And there's even a solid material of plastic that represents this water. So it's called solid water as a trade name in this Phantom. But we have polyethylene at minus 97, acrylic about 120. And then obviously there's an air plug, and then bone, approximately 910. Teflon's used a lot, and a mix of Teflon sometimes to emulate bone changes by each manufacturer. Also, the center of that Phantom, we see the number of pins in here. Those are spaced at about 0.5 millimeters, so we can even ascertain slice thickness. Also, do we represent distance very well in the image? So there's an example of 2 pins being 100 millimeters apart. Can we measure that on the scanner? Okay. And then what you see down here is these different resolutions. This is actually low contrast detectability. The material that's representing this 25 millimeter element here is only 6 CT numbers different than the background. And then we also have a number of line pairs that are represented here in this scaling system as well to verify resolution. So this Phantom is independent of any OEM. Okay. In Europe, they use the Kaplan Phantom to do the same thing. So a very rudimentary block diagram of a CT scanner, obviously, showing the X-ray tube. Collimator is not shown there, but then basically ISO center, where item number 24 is imaginary center of the gantry, and then the detector pointed back towards their focal spot in the X-ray tube. And then we have the A to D conversion called the DAS that converts that analog value to a digital value and then sends that over for our image reconstruction. It's saved to hard drives as we scan around, and then we can back project that data and apply filters and other compensation as well. And so we have to deal with an X-ray tube, an X-ray controller. We're spinning the gantry. We're also moving the table at the same time, and we're under computer control to manage all this. And then we have the operator that's basically derived the which algorithms want to be used. Okay, we pick which filters, where the table needs to be, start, stop, the slice thickness, all those done in our protocols. That's sent to the computer, dispersed out as a job. And then we have 2 types of images. We have raw data image that's in the image reconstructor chassis, and then we have the mass storage of a completed DICOM image. So the DICOM images are already processed data, whereas the image data that we have, or raw data we have in the image constructor, is that raw data that we can reprocess again with different algorithms. Here's an example of a GE VCT that represents a true block diagram of a product that's out there. We actually have one of these as a bay. And then if you come to training here, this is one of the systems that is also used as training as well. So you can see that we have a little bit more detail, but we still basically have the same elements: an X-ray tube, X-ray generator, filament control, KV control, high voltage tanks, and then we have a collimator that manages the aperture size, and then also we have different filters in there. And then we do a detector element, and a detector, basically the crystals and the photodiode behind them are very temperature sensitive as far as swing. We have leakage currents, those kind of things. So we try to maintain that temperature range that those operate in a very precise way. Each OEM has predicted what kind of temperature they like to keep that at. So the gantry gets hot inside, but we want to cool it enough. We don't want it to get too cool that the detector can't stay in a stabilized temperature zone. Then we do A to D conversion, and then data comes back out. So we have the rotating controller that's called the ORP. ORP, that's onboard rotating processor. It's controlling everything on the rotate frame, stationary controller, and then the controller that's in the table. So it's got 3 master controllers, and subsystems will be reported as errors or functionality issues would be reported back to those controllers to the host system. So if you notice, we have a recon over here. So we have what we call a DAS interface processor, DIP. A lot of acronyms in this world for CT. Each OEM has different acronyms for somewhat the same functions. So it's OEM centric as well. But the basic design of a CT scanner is somewhat the same. So this goes into more of a flow perspective of how we're moving the data and the control. So we're using slip rings to communicate as this gantry rotates, and this gantry will do 0.35 seconds. So it's very fast for cardiac runs. It's a 64 slice system. So this system was released to the market 20 years ago in 2005. So still viable today. There are still installed systems with regards to that. Their computers have been upgraded for advanced processing features, but realistically, that scanner still is a very functional scanner with good image quality. So the recon part is what's been upgraded. The computers and recon have been upgraded a number of years to improve the functionality, the speed of image reconstruction, also the advanced features that we're coming to market as well, that we'll discuss a little bit farther along in time. But so we have a number of computers. High-speed DAS data is what this bottom one is. This is the raw data array that these 2 computers, the DIG and the VERB, will process for image reconstruction. And then that completed image will be sent to the host for display, and then the DICOM images there will be transferred to a hospital DICOM server on the backbone. So X-ray tubes. X-ray tubes, we know they're only about 2% efficient, and that's at the target. So 80%, 98% of the energy goes out as heat. So rotating anode tubes, if you've been involved in CT theory, really dissipates the energy, but the focal spot right here has remained the same most of the time. Most X-ray tubes used in CT have a 7-degree target angle. When we get into the scanners that are 128 and higher, especially the 256 ones, that will change to 11-degree target angle because of the spread getting to all the rows of detector elements. So we have a rotating target, tungsten target. This shows 1 filament. Most X-ray tubes have 2 filaments. Resolution-wise, a smaller filament is the advantage, but it would burn our target. So at some point in time when we're doing larger body studies, our resolution is not as important as getting the whole body in, so they'll leverage the large filament for those types of studies. But we're dealing with voltages of 140,000 volts potential here on this setup right here. So if you think about it, in CT, we're dealing with computers with a memory voltage of 1.5 volts, and we're going all the way up to potentially 150,000 for testing, but we typically max at 140. So this is an example of VCT's X-ray generator. We're taking line voltage about 700 volts nominal, converting it into AC, and then rectifying that AC with a tuned circuit to give us our voltage up to 140,000 volts. On this tube, it's a single cathode connection with 140 on one cable, and the anode's grounded. But in other scenarios, we have a plus and minus kV that equals 140,000. So this generator is 100 kW, so we know 2 kW will become X-ray, the other 98 kW will become heat. So obviously a lot of fans in the gantry, making sure the room is environmentally good with dissipating the heat. And we have, obviously, we get high voltage arcs from the X-ray tube, but also the high voltage tanks and even the high voltage cables. So we have to be very delicate in dealing with all this material as well. So this is an example of a detector. What's not seen here behind this metal plate is actually the detector crystals. They're kind of behind the plate here, but these are the converter boards behind it that receive our detector data and then convert it into A to D, and we have a number of rows. So this one has an example of 57 modules. Some of the modules in the center will probably have a tighter spec than the ones towards the outer edges. So they might be graded like A, B, C, regards to the detector functionality and which ones go where, okay? So if you think about it, we've got 64 rows, right? And we've got so many channels, and we're collecting this data, about 984 samples per gantry rotation. So that's less than a third of a degree of data that we're collecting around as we're rotating around the patient, okay? So we talked about filtered back projection, but on newer machines, there's actually an arena reconstruction that is used as well. So it's used not just in CT, but other ways as well, because it's calculated. But basically, instead of just having the filtered back projection data, we can take some of that raw data, reprocess it again, and try to remove noise. Essentially, what we're trying to do is remove the noise, and in the process, sometimes we use MA. Higher MAs will give us better sampling. Think of the more MA, the more X-ray photons we produce. So if we sample better, we'll have a better image quality. So if we try to reduce the noise in the image. So one of the ways was to increase MA, which would increase dose. With iterative reconstruction, it allows us to reprocess the data a number of times using math functions and resampling some of the data to actually reduce the noise instead of using higher MA. So a lot of them, Philips calls it iDose, GE calls it Acer, Siemens calls it Iris, and ADAR. So depending on how much they want to process, which will, and change the reconstruction time, we can actually reduce less noise in the image. So it's a new approach. It's an option. It's leveraged. When we do image quality on CTs, we don't do this because this is a variable that can change. But when we are looking at patient data, we want to lower dose. So I can use this function to lower the dose and maintain the same amount of noise, or I can use this at the same MAs and increase the image quality better. So it allows us to do it, use it in two ways, and which is what the radiologist at the hospital will decide to do with the protocols. So the example that you see on the left of half the screen here, we have noise elements in here that as we go back and increase with iDose in this case, we can reduce the noise. So false positives, when you get some of these areas where it's a little murky, it could be you check the CT number, it could wind up being misdiagnosis cancer or something like that. So the more clarity we have to the image, then our less noise, we can better diagnose the problem the patient has. So another aspect of newer technologies is multispectral. So if you think about it, if you have one tube shooting 80 kV, another X-ray tube shooting 140, well, what would that mean? Well, 80 kV or lower kV energies would get absorbed more by soft tissue than bone and those kind of things. Whereas 140 will penetrate through them a much, faster, I guess is the best, not faster, but be less attenuated. So with those two spreads you can see in energy spectrums, then that allows us to look at soft tissue and enhance what we see with iodine and calcium as well. So there's different approaches to approaching dual energy. Two tubes is being one. Another one is dual layer, where I have a detector that would basically disseminate soft X-rays, which were lower KVs, to hard X-rays that would penetrate deeper into the detector. Okay, and then rebinning, you could scan the patient with a low technique and then rescan them with the high technique. And then there's KV switching, where alternate views are collected at different KVs. So the approach is a little bit different by each manufacturer to get the dual energy, but what you get is what we see here in multispectral imaging. So it better enhances iodine, and then obviously you can see that we will better discern soft tissue when you overlay the data sets. So it's better for soft tissue enhancement to see small differences in CT numbers that we would see with soft tissue, okay, which is basically our anatomy, right? So common issues with CT scanners. This is our cost to serve when we're starting to look here. X-ray tubes are one of the highest failure items. Not that they happen there regularly, but it's from a cost perspective, it's one of our highest issues. We're talking about X-ray tubes anywhere from, mid 50,000s all the way to 240,000 based on the scanner. Along with that, obviously, we're dealing with high voltage arcing because we have a vacuum inside that tube. Maintaining that vacuum is hard. We also have other issues with the rotor itself. We're trying to dissipate that energy on with a rotating anode. The bearings wear out. Remember, we're slinging it around the gantry at high G's as well. Then we have extra generator parts, especially the high voltage tanks. We're dealing with 140,000 volts there. And then the inverters that feed those tanks. If the tank breaks down or its high voltage circuits break down, it could put extra stress on the inverters and take them out as well. And then the other side of the coin is obviously on computerized tomography is the computers. We're using them quite frequently. We're using them in the subsystems. We're using them in reconstruction for designations of a scan, and then most of them still use old conventional hard drives. Even though they're running at 10, 15,000 RPM drives, there is a new movement into the computer space with newer types of SSDs and those items used as well. And then we've detector modules. Crystals do not like radiation. So one of the things that happens over time is the center detector elements tend to go first because they get more X-ray, and that those modules degrade over time. Once they degrade at a certain rate, our image CT number attenuation coefficients are hard to detect, and so we'll wind up replacing those defective modules and then recalibrating the machines. Okay. Then we're rotating that gantry. Sometimes the gantry, the rotating part itself is over 3,000 pounds. So we're accelerating it, we're changing its speed, depending on the type of study, and then we're stopping it, okay? And then one of the least problems that we have, other than the covers maybe on tables because of gurney strikes, is table errors. Because typically when we do a scan, we just lift the table up to a given fixed location and then move it in and out. So I'll go back to this for a second. So really the horizontal part of the table movement, some tables have dual elements to get the distance to travel through the gantry. Other times you just have one table controller using it all. So obviously we're using that every study, just as well as rotating the gantry. So when we deal with cost to serve, there's a big push by a lot of groups to go in-house with regards to their programs instead of doing full service with OEMs. And then there's obviously independent service providers as well, what we call ISOs. So AllParts has the ability to support those. And with regards to doing that, we have a number of CTs here that we do for evaluation of parts, but also we use and teach on them as well. So parts that normally might be just bench tested with other vendors, we actually put them on our machines and scan with them here to validate image quality as well. So that might be a differentiator as well. But from a cost perspective, whenever you're looking at servicing a scanner, tubes are, when I do a program for a tube, I'm looking at cost to serve, benefit analysis of what to do direct service on. The weighting factor is, do I have an X-ray tube available? And what's it cost to do a service delivery plan or a business plan? Also, are the parts available to support that X-ray tube? High voltage generator parts, tanks, and then computers, and then how many hours are dedicated to PMs and service calls, and then training. Training is one aspect a lot of people kind of have a misconception about. Training can reduce your cost to serve because instead of replacing 2 or 3 parts, you would replace 1 in most cases. Sometimes you have to replace 2, but those parts are usually the lower cost in the end, like a transmitter receiver that we have on the slip rings. Those 2 parts may be 10 grand completely, 5 each. So ordering both of those, sometimes troubleshoot, is much easier than being down an extra day waiting for a misdiagnosis on a part. So, but training and parts are two of the aspects that reduce our cost to serve. So some of the things that we have with regards to GE is we have alternate glassware available at AllParts for that. And some of these examples are tubes. There's the Optima 540 is not shown on here, but that actually has a liquid bearing tube as well. That so GE and a lot of manufacturers have gone from metal ball bearings to liquid metal bearings. So that changed the technology and some of the parts leverage for some of these machines. So it's a newer technology for some of the GE scanners. It's been in other OEMs for a while. Okay. So we have a Revolution EVO and Optimus 660 here at the office that we tested third-party tubes with as well. So all the tubes that we use or sell have been tested, have been validated here as well with regards to the manufacturers. So we have QA bays. So in the G side, we have the Revolution EVO, Optimus 660, Brightspeed 16, a Lightspeed VCT. We have two of those. They have two versions of detector in them, and to support those two versions and parts, we have two versions. And then we have a Lightspeed 5X platform. That's probably the oldest. That came to market in 2003. So a little long in the tooth, but still viable in the marketplace. In Siemens, we have the Emotion 16, Sensation 64, Definition 128, Perspective 64, and we just added a Go Up and Go Top systems into our bays as well. So we have a number of people that work in the service aspect that use these parts in the field. But with regards to it, we believe in making sure that machines, all the parts that come out of here, have been scanned on a real scanner first. That's why we have the diversity of the number of machines we have, and we get to leverage them for both repair and also testing and validating tube providers that provide X-ray tubes to make sure they meet OEM specs. And then that way we can put them on a shelf, knowing that they'll operate and reduce downtime in the field. So Philips multi-vendor uses parts from AllParts as well as third parties. So we find it very effective to reduce the DOA rate. Sometimes things are damaged at shipment, but our DOA rate is very low at AllParts. So if you want to find out more about AllParts, they have the search page here at allpartsmedical.com. Then we have CAT scan parts. We also have other items on that website too. AllParts supports not just CT, but some of these are our training courses that we have in place. If you're interested, the calendar will be on the website as well at allpartsmedical.com/training. And then obviously CT, RNF, portable X-rays, C-arms, a venue of parts. The operation here in Nashville has two different buildings. The building that has all the bays is 80,000 square foot, and the other building that hosts all the parts on the shelf and ready to ship is probably 90,000 square foot. So quite a big operation here in Nashville. So if anybody has any questions, be glad to address them.
Perfect. Thanks, James. We've got a couple that have come through. The first one is, as metal can't be inside an MRI room, what objects or elements can't be in the CT room or in or on the patient?
Well, metal is a problem with regards to getting artifacts from the metal, because if you think of the attenuation coefficient of bone being in the high 900s, metal would obviously be higher. But newer scanners have options to reduce the metal as far as being part of the image. When you go out of the range of the bone in that perspective, we might cap the CT number attenuation to less than that. Fillings are a big problem on CT. People that had older amalgam fillings. So what we would do is they came up with a metal artifact reduction option that when the CT number goes to that high a range, it's basically tied to when the CT number moves into the range that is back to basically slightly above bone. So it reduces the number of image artifacts. And so if older machines where they may have fused your back with metal screws, which are typically stainless steel, they would cause artifacts. On the newer ones, we can even reduce the artifact, but you can even see the head of the screw now. So it's much improved with the newer algorithms.
Okay, another question that's just popped up. With all the new CT technologists, how are we going to stop providers from over ordering scans because they want to utilize it? Have you got any
Well,
opinions on that?
well, I don't think they're going to overutilize it. I mean, an example that I have with my wife is she went to ER for one issue and was scanned, and then they ran it through obviously an AI program and found something that had been missed before about one of her vessels. We went to an internist to discuss it, and then in 2015 she had had a scan. They called up that scan and looked at it and said, well, you had the same problem then that we didn't detect, and there has been no change. So typically, I think you're going to see more of the latter, where older images through AI analysis being used to analyze current images is being leveraged to say, you might have a problem here, let's check it and go back. Hopefully, if you have older scanners that actually would show that problem. So that the doctor basically explained to us that they're seeing more referrals for older problems with CT, not newer CTs being ordered.
Oh, great. Okay, another question here about your opinion on liquid-bearing CT tube versus metal-bearing tubes. What do you think the advantages and cost, or how much more life would liquid have over normal bearing tubes?
Well, I think it's dependent on the OEM. Okay, with regards to some of the Siemens systems, they've had liquid metal tubes, like the Emotion and Perspective, and then GE's used typically ball bearings and moved into liquid bearing. Haven't really seen an increase as much. Now, what the liquid bearing does is it allow tighter tolerances. So one of the things it does with regards to image quality is you have less float of the insert or the target that might over a period of time in a ball bearing tube loosen up a little bit and maybe generate some image artifacts or ISO, what we call ISO. ISO center problems with regards to image and looking at resolution, whereas the liquid bearing seems to last longer with regards to image quality. But tube life in itself has so many other aspects, the heat load, metal vaporization, those kind of things that we haven't really seen that big a disparities and distance as far as tube life. Okay, not one doubling the other or anything like that. So the cost benefit ratio from replacing a metal ball bearing tube versus liquid metal bearing tube is more expensive, so it almost washes in a cost perspective. Okay, but it is a better design.
Perfect. We've got time for one more question, and it's what are you most looking forward to in new technologies with CT?
Well, I think as you've seen with some of the newer images, isotropic imaging, where the thinner the cut, the better represented in 3D. I always thought that even 5 years ago that eventually, instead of a doctor looking at an axial image of a patient or even AI looking at it, if instead you could have a volumetric data set in the DICOM space where you could rotate the patient, look at any dimension with computing power getting strong enough to have 3D DICOM, to me was always the pinnacle from going back to looking at a patient, how they really look versus how they're dissected with CT images. To me would be the ultimate goal, but I had hoped for that 5 to 10 years ago. So I hope we'll get there one day.
Perfect. Well, thank you so much, James, for your time today and for such a great and informative presentation. And also thank you to AllParts Medical. Please visit allpartsmedical.com for more information. Now, as promised, the answer to today's trivia question is brown. So congratulations to our winner, Madison Corhag in Kentucky. Now, just a quick reminder, you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 Art Category A CE credit by the AHRA, and you'll be able to download the certificate directly from your computer once a survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Please visit icewebinars.live for more details of all our upcoming ICE webinars and, of course, complimentary registration. And if you've missed any of our past ICE webinars, please visit icewebinars.live to view our whole webinar archive. So thank you all for your time today, and I hope you enjoy the rest of your day.